Yes, so I'm the chief scientist of Netronome. I'm responsible for pretty much the silicon architecture for the chip that's sitting on here. You'll have Johan Tonsing talking in a little bit about the software, and then he'll get into the labs themselves. I would like to just get ourselves sort of moving on what it is that actually is making the engine inside here. I'll be talking later with some of the labs again about the low-level detail. You can ignore me if you really want to, if you're interested in the very, very high level of things, how to program in P4 and so on. But I will tell you all about how the engine goes, how many cylinders it's got, how fast it goes, and why it goes fast, in some sense, and help you understand why it goes well. There are a number of ways to build a network processor. The simplest, in a sense, is a fixed pipeline. So here we have a fixed pipeline. Actually, in a sense, it's a NIC. Could be just a network processor in the wire. But we have MAX and PCIe delivering packets into a pipeline. And you'll process this going through a pipeline. Maybe you'll do virtual port detection. You'll do some access control. You'll do some metering. You'll do some management. You're going to end up and deliver it to the appropriate destination. And there are certain stages along the way. And you implement one stage at a time. And in a silicon architecture like this, it's actually fairly readily built. You hard code individual features throughout the pipeline. It's a nice rainbow. You do your red stuff, and then you do your orange stuff, and then you move on and eventually end up with the purple bits at the end, your indigos and your violets, and you deliver it. And this is fantastic if it does what you want. Not particularly programmable. If it doesn't do what you want, you can't really get there. So an alternative, a step forwards in some sense for those people who want more flexibility, is a configurable pipeline. Configurable pipeline will let you take packets in. You can do your first part. Maybe your red and your orange can be done together. You do a bit of red, you do a bit of orange, bit of red, bit of orange, but you've done that stage before you move on to the yellow and the green. In a configurable pipeline, you can do this. The very simplest match action processor architectures, network processor architectures are like this, the very simplest ones. It provides more flexibility. You've got initial characterization, perhaps, in the red and the orange, a little bit of trade-off, a little bit of statefulness there. You've got a MAC learning. And then you can pass it off to the next level of access control or whatever in your yellow and green, which can again be somewhat stateful. And you can move forwards and you can do all the steps. This is much more flexible. It doesn't necessarily mean you can do everything you would like to do. Netronome has a different architecture. Netronome's architecture has come from the network processor family of devices that Intel developed back in the early 2000s. And it's based around having a set of worker threads, a set of worker processors that are there to do the hard work. They're there to be programmed to implement your pipeline. So an individual worker will do the red, the yellow, the orange, well, hopefully red, orange, yellow, red, orange, yellow, green, blue. He will run through the rainbow, and potentially it can run through the rainbow twice, or it can repeat whichever bits it wants if it's doing tunneling and so on. And the workers will be running each packet to completion. So the packets here are not processed in a physical pipeline. They can be processed in a software pipeline. Being a software pipeline, you can repeat whichever sections you want. You can repeat nothing. You can skip sections. One of the tricky parts here, though, is for this to work effectively, you have to be able to share state between those worker threads. You can't just let them run individually. There's generally a lot of shared state. Maybe it's a cache of the active flows that are there. Certainly statistics have to be managed. Meters have to be managed and so on. So Netronome's architecture isn't just you give it to a lot of CPUs. Really, certainly from the silicon perspective, the center of the universe is not the processor. The center of the universe is the transactional memories. Transactional memories are memories that include an ALU, or a number of ALUs. They include a processing pipeline. A very simple processing step that a memory can do is a statistics operation. You ask a memory to say, here, I received a packet, it's 17 bytes long. Can you add that statistics to statistics for a virtual route of 5? It's at this memory address. In which case, your transaction is do a statistics operation with this stat of this amount. The transactional memory can then do all the work that that entails. It can be read the memory, update the byte count, update the packet count, do any saturation, generate any events that need to be done if the counters overflow, and store that back into the memory. Possibly, for transactions such as metering, you're doing all of that work, but you're also reporting back, as a result, the color of the packet. So for a transactional meter, you'd say, I've got a packet, it's just 17 bytes long. Can you use that meter over there with this standard, RSC 2698, whatever, and the input color is orange. The memory has to read the meter contents, do the ALU operation, which is pretty easy. Come up with a new color, a new meter value. It's consumed a certain amount of the rate. It can write that back into the memory and report on the color. Netronome's architecture is driven around having these transactional memories and these seas of workers. We have a vast array of transactional operations that can be performed. And it runs very fast. The actual implementation is like this. This is the block diagram of the chip. Now, as I said, if you're doing P4 at the top level, you can ignore all of this. So this is as deep as we get into the actual physical block diagram silicon you'll get to see. But it is worth seeing what's inside, what's under the hood. This is the silicon architecture, the silicon design, as it were, of the chip that's on the cards that we've got that we're using today next door. There's a lot on the diagram. This is a 3 billion transistor chip. It's big. It's on 22 nanometer, as Neil told us earlier. But it's broken up into individual islands that do the work. The whole thing is broken up into small islands. It's not actually 3 billion transistors. In a sense, it's 30, 100 million transistor chips. And I just want to really highlight the one in the middle. You can see the rectangle in the middle has got, well, this one's got 10 FPCs. Those are our processors that are sitting inside an island. The processors are multi-threaded. So we have threading inside those to manage multiple threads of processing at once. And they're tied to memories that are at the bottom of that rectangle there's a memory on the left of that rectangle at the bottom called the cluster target memory, and there's a memory on the right called the cluster local memory. These are the transactional memories. There are local transactional memories within an island. Actually, later in the day, in lab 5, I'll go into a bit more detail of the programming of some of this, which, as I said, is not important if you're at the P4 level, but it's nice to know what's under the hood here. The other areas that are of interest, there are memories at the top and the bottom, transaction-optimized memories. These internal 4 megabyte memories that let us do lookups and statistics. One of the things that's important when understanding how the internals works is that there are different classes of transactions that you might want to do. Statistics is one class of transaction. I may want to do 10 different statistics for a single packet. It belongs to a port, a virtual port, a flow, and so on. It belongs to a number of different memory locations, a number of different statistics. A different class is a simple atomic operation. A simple atomic operation can be an atomic bit set, test and set. it can be a atomic add, or it can be something more complicated like a hash table, lookup, add, insert, tell me where you inserted it into my hash table, which is just, again, it's part of an atomic pipeline. So each of the large memories has a set of ALUs, a set of processing engines that let us do different things, like stats, atomics, reading and writing, and recursive lookups, algorithmic TCAMs, and so on. So the memories, these are the transactional memories, again, that are doing the hard work for the stuff under the hood. Finally, and there's a lot more on here, but the two bits that are really useful, how do you get packets in and how do you get packets out? We have packets that can come in on the top left. That's the network interface side of the world. A packet comes in, it is delivered through various pieces of hardware that do characterization, checking checksums, checking CRCs, checking packet types, programmably looking at it, so we can program to look at MAC tables and so on. And packets will then be delivered directly to a particular processor. Remember that we have a sea of workers. The workers are saying, I'm part of the sea, and a packet will be delivered to one of those workers that said it's ready. And it'll be running in one of these FPCs. The other side of this, packets in and out, well, we can transmit packets through the network, in which case they kind of go back in the other direction. But the other side is, we're obviously focused as well on being a NIC. We support a lot of virtual functions, a lot of, let me say, a lot of the PCIe functionality and the device driver functionality, it's a software world, and we'll come on to that in the software side briefly, I'm sure. But you have to have the hardware that makes it go. So we have hardware in there that includes more of our we program them ourselves, FPCs, to give ourselves good device drivers to provide us with a 40 gigabit NIC capability. So we've got PCIe capability on the right-hand side and network on the left. And finally, the bit that I missed earlier, we do support the transactional memories. We have also got external memory for transactional memories. We can support up to 24 gigabytes of memory attached to the device. So we've been designing this with the capability to have large flow tables and large tables for statistics and so on and so forth. It's not just a small integrated device. It's capable of having additional external memories as well. As I said, this has been a deep dive into kind of the silicon architecture. Usually I talk for hours about this, but you're going to be saved from that. I'll be handing off now to Johan Tonsing, who is the chief software architect, and he will go into why you don't need to care about any of what I've just said.